In this video, we want to emphasize decrease and conquer technique. The decrease and conquer technique is based on exploiting the relationship between a solution to a given instance of a problem and a solution to its smaller instance. Given a problem instance, if we can reduce this problem instance to smaller instance of the same problem and solve this smaller instance with the same approach, expand the solution of smaller instance, extend the solution of a smaller instance to obtain a solution to original instance. If we could find this beautiful relationship, then we can implement through top-down decrease and conquer or bottom-up decrease and conquer. Let me explain what is this relationship, and let me draw here. So we say give a problem instance. Let's use IN to represent that. Corresponding to we have n items. Find a solution, find the algorithm, or execute the algorithm, right, to solve this problem. Let's say we have algorithm ALG to solve AN. If we could find out this algorithm of AI can consist of, is composed of ALG AN minus AN prime, right? Let's say AN is N prime. The N prime smaller than N, right? If it's same as N, doesn't make sense. It's smaller than N. It consists to this step, and also this is equal to, right? Equal to this step and this step. Another step, it is combine or extend what we have this solution and to obtain the final results, right? If this step, the second step, if this step very straightforward, if this is straightforward, in that case, to solve this problem, change to be solve this problem, and this straightforward way. In that case, we can use a decrease and conquer. There are 3 steps of decrease and conquer. The first one, decrease by constant, is also corresponding to if you have n minus n prime is equal to a constant. So every time in each iteration, this is a constant. In each iteration, it will reduce the problem instance with the same constant. In that case, we call decrease by a constant. The first step is A. And B, decrease by a constant factor. And corresponding to n corresponding to n prime and divided by n is corresponding to some constant. Let's use k to represent, and k is smaller than 1, larger than 0. In every iteration, you want to make sure when you reduce the problem, you reduce the same ratio. And with corresponding to, for example, you have A1, A2, AN sequence. You want to sort this sequence, right? You sort this sequence and you reduce to be, every time you reduce to be the half. You say, okay, I want to solve this one. This is A1, A2. I want to sort to AN divided by 2. And you want to sort AN divided by 2 plus 1 to AN. Next iteration, you cut into, every time you use the same procedure, right? So you want to sort A1 through AN divided by 4. And here you have AN divided by 4 plus 1 to AN divided by 2, right? Same thing here. You want to cut into smaller instance. You follow the same procedure. And in each this procedure, you remember to combine the results, right? So this is decreased by a constant, and also it corresponding to divide and conquer method. The third one corresponding to variable size decrease. The variable size decrease corresponding to the size reduction pattern varies from one iteration of the algorithm to another. And I use this load as example corresponding to, this is the third one, decrease variable size decrease. So the size reduction pattern varies. So corresponding to, what do you have here? The n prime and n, the difference between n prime and n is not consistent. Sometimes big, sometimes smaller. Okay. So this is the 3 types of decrease and conquer. Now let's take a look. Use this example, computing A to the power of n. The brute force, let's use those because it's more clean. So let's see here is we need to check for compute A to the power of n. The brute force, in a brute force corresponding very straightforward approach, and check the problem description, and to say that here, if we want to calculate AN is equal to A times A times A, we have NA. And such that use looping, use a for loop, and it means multiply A by n times. So this is a count-based loop. Obvious, right? And the second one, this is the first one, brute and force. And the second one, we check divide and conquer. This divide and conquer very similar to what we talk about, decrease by constant factor. And this corresponding to, for example, you have AN with, okay, in each time we want to calculate A to the K, right? And we have multiple A to the K, and the last one, let's see here, right? We have N divided by K times, we use a floor, and times A let's go to the n modulus by k, right? We see this problem is reduced to calculate a to the power of n is reduced to multiple a to the power of k, right? To solve a to the power of n, we have to calculate n divided by k times we have to calculate a to the power of k for n divided by k times, right? And also we have to combine the final results. Combine final results with a k and k flow, and also we have a n modulus by k, right? This is what we need to do. And you can see this divide and conquer is divided to different groups, and each group has the same size of instance, for example. And this is decrease, divide and conquer. Now let's take a look if it's decreased by 1, by constant. So in that case, we can treat this problem. We want to calculate a to the power of n equal to a to the power of n minus 1 times a. So to solve this problem, a to the power of n, we say we needed to solve a to the power of n minus 1, right? And then combine the results, or extend these results from a n minus 1 and the remaining 1a, right? 1a. So this is decreased by 1. And also let's take a look if it's decreased by constant factor. For example, half, right? Then in that case, so this is the fourth method. And we say to solve a to the power of n, we can reduce to be a to the power of n divided by 2 times a to the power of n divided by 2. You may say if this is not divisible, what do you do? Then in that case, one is floor, one it is ceiling, right? So you can see here is the same approach, but work on different instance. Okay, so this is decreased by constant factor. So based on this explanation, I think it's very clear. Now let's take a look. One example corresponding insertion sort. This is still for the same for the sorting problem. And last time we already talked about the sorting problem, right? Given instance, given a sequence of numbers, of course you can use it for any objects. Once these objects can be comparable, let's say we have a equal to a1, a2, and an. We want to find a permutation or reordering. And we have a prime equal to a1 prime, a2 prime, and an prime, right? Should have the same number of elements, but the order is changed such that a1 prime smaller than a2 prime and smaller than am prime. Right? So this is a sorting problem. And last time we talked about selection sort, Barber sort, and today we want to check for insertion sort. And you will see this exactly is a decrease and conquer. To sort array A, N0 through N-1, and we recursively resolve the sorting A0 through N-2, and then insert A N-1 in its proper place among the sorted A0 through N-2. For example, let's say we want to sort, usually implemented bottom up, long recursively, sort 6, 4, 1, 8, 5. To sort this one, and we want to check if the previous 4 already sorted, then we can insert 5 to the proper position. If you sort this 4, you want to make sure the previous 3 has been sorted. Then you insert 8 to specific location, right? So you can see every time you assume every time you reduce one element. And in such case, you can see here, since this is from bottom to up, and you check, when you implement from the bottom to up, and you check from the index 0 through index 4, and this 6 you do not need to change. And then when you insert 4, every time you assume the previous already been sorted, right? And then you insert 4 to the previous local sorted sequence, and you want to swap it, and such that you have 4, 6. Then you want to insert 1 to the proper position, and you check 1 with 6 and check with this one, right? Every time if it is larger, you swap to the next position, and you have 1 to be here. And then you insert 8. When you insert 8, same thing. If this one already larger than 6, in that case, this is a good position for that. You don't need to change. Then you insert 8, 5, and for the same thing, you want to check this 5 with 8. If it's not good, you move 8 to next position. Check 5 with 6, move the correct position. Check 5 with 4, that's not larger than that. You put a 5 here and keep the same previous one. So this is the insertion sort. The algorithm here corresponding to, since you want to check each, you want to increase, you use a bottom-up method. In each method, you assume the previous element has been sorted. It is starting from, you can start from the 2 actually here. In the textbook, it is starting from 1. Also, that is also good because the starting index is 0. Starting from 1, go through the last element, and every time you want to insert this element to the proper position in the previous sorted list. And then in that case, you just need to insert this element I into the proper position. So you can see this is very obvious. And from here, you can check what is the time efficiency. Let's just write it down here. Okay, let's check for time efficiency or time complexity is the same. First, we check the input size. Definitely, it's go to the A length. Let's use N to represent Second one, basic operation. And we check basic operation is related to element A and also contribute the most. And we have a for loop, we have a while loop, and definitely we count for that, right? If you don't like this way, you can just count the each statement, the frequency of each statement, and sum them up. And we see here, this outer loop. In the outer loop, we see this is how many times we need to invoke a specific statement, right? So we have I equal to 1 through n minus 1, right? We should be capital N. And inside we have one statement plus one statement plus here the for loop. In the for loop, we check what is the specific case if in this number is in element I is greater than the previous element or not, right? So in this one, you can list here. You have different possibility. One possibility, if this number always larger than the previous number, in that case, you just have one comparison, right? Let's put it here. So this is the best case. And this is plus 1, right? So we check for different cases. We just help you to analyze that. And if this number always, the best case corresponding to the already sorted list. And worst case, let's write down worst case. If the worst case, then you have to check for every previous steps, right? So in that case, it is how many, if I is equal to 1, it means the previous have 1, right? So it's sum up I equal to, so it should be j equal to 0 through I minus 1, right? This is also the case. And then, based on this analysis, we write it down, best case. Worst case, reverse order, right? Best case is ascending order already. A is in ascending order. In that case, the runtime of this algorithm is equal to I equal to 1 and minus 1, 4, right? So in that case, is big O n. Worst case, corresponding to A actually is in a descending order. It's opposite, it's reverse order, descending order. In such case, you have to make sure you switch each element to the next position. In this case, Tn is equal to I equal to 1 and minus 1 is 3 plus j equal to 0 through I minus 1, right? So if you're familiar with what we did in previous step, then we have O n square, right? So this is for worst case. This runtime analysis for worst case is for the best case. Okay. I think we solved this one. And the space efficiency, in this case, we use the same array, so it's no problem. And the stability, the answer is yes, right? The elements, if they are the same value, the element in the low place will still stay in the low place in the sorted results. And the best element sort algorithm of all ballerine insertion thread. Okay, I think that is all.